You are here. You feel the weight of your own body, the gentle pressure of the air on your skin, the solid ground beneath your feet. You believe in this world. You trust it. You trust its objects, its textures, its apparent reliability. The chair you sit in is a thing. The water you drink is a substance. The hand you raise before your face is your own, a solid, predictable presence. This is the story you have been told since birth. It is a story whispered by your senses, confirmed by every interaction, and solidified by the language you use to describe your experience. A world of things. A reality of separate, distinct objects. But what if that story is a lie? Not a malicious lie, but a necessary one. A convenient fiction. A grand and beautiful illusion sculpted for beings of our scale. A user interface for a reality so profoundly strange, so deeply counterintuitive, that to perceive it directly would be to lose your footing in the world you thought you knew. What if beneath the placid surface of the material world, there is a hidden kingdom, a realm governed by laws of such bizarre and paradoxical character that they mock our conception of logic itself? And what if the denizens of this kingdom, the very architects of your physical form, are creatures that defy the most fundamental rule of all, the rule that a thing can exist? These are not creatures of flesh and bone. They are not the curiosities of the animal kingdom that stretch the boundaries of biology. They are something far more fundamental. They are the ghosts in the machine of matter. They are the prisoners in the heart of the atom, whose eternal confinement is the very source of the world's solidity. They are called quarks, and their story is the story of everything you have ever touched, everything you have ever seen, and everything you are. To understand this, you must be willing to let go. You must be willing to question the evidence of your own senses. You must follow us on a journey inward, past the familiar landscapes of your own body, past the cells, past the molecules, past the atoms themselves, and into a core so deep and so strange that the words we use to describe it begin to break apart. Are you ready to see the lie? Look at your hand again. It seems so definite, so unquestionably real. You can make a fist, feel the tension in the muscles, the pressure of skin on skin. It is an object separate from the air around it. It has boundaries. It has substance. This is the great illusion. It is the first and most profound deception. Science began to peel back this illusion centuries ago. It told us your hand is not a single, continuous substance. It is a bustling metropolis of cells. And each cell is a complex factory of molecules. And each molecule is a precise arrangement of atoms. Here, the illusion of solidity already begins to tremble. For what is an atom? We are taught to picture it as a tiny solar system, a dense nucleus orbited by zipping electrons. But even this is a convenient cartoon. That nucleus is unimaginably small. The electrons are not little planets on fixed paths. They are shimmering clouds of probability, ghostly smears of potential, existing everywhere and nowhere at once until the moment of interaction. If an atom were scaled up to the size of a cathedral, the nucleus would be no larger than a grain of sand at its center. The rest, the vast, cavernous space of the cathedral, is the domain of these electron ghosts. It is, for all intents and purposes, empty space. Your hand, then, which feels so solid, is overwhelmingly, astonishingly empty. The feeling of substance you experience when you clap your hands together is not the meeting of two solids. It is the electromagnetic repulsion between the electron clouds of the atoms in your left hand and the electron clouds of the atoms in your right. You have never truly touched anything in your entire life. You have only ever felt the force fields that prevent you from passing through the ghost-filled emptiness of other things. This is the first layer of truth, a world made not of substance, but of forces and emptiness. But this is only the beginning of the journey. The mystery deepens. We must go further. We must venture into that grain of sand at the center of the cathedral. We must ask what the nucleus is made of. The nucleus is where almost all the mass of the atom resides. It is the anchor of its reality. It is composed of particles you have heard of protons and neutrons. For a long time, this is where the story ended. These were thought to be the fundamental, indivisible building blocks of the atomic heart. Solid little spheres of being. The end of the line. But the universe is rarely so simple. It guards its deepest secrets with layers of complexity, each one more paradoxical than the last. The universe refused to let the proton and the neutron be the final answer. To understand why, we must leave the quiet interior of the atom and travel back in time to a period of exhilarating chaos in the history of human thought. We must go to the middle of the 20th century. The year is 1960. The world of physics is a mess. It is a jungle overgrown with strange and unexpected discoveries. Scientists, having built powerful new machines called particle accelerators, were smashing atoms together with tremendous violence, hoping to crack open the secrets of the nucleus. What they found was not elegant simplicity. It was pandemonium. Out of these collisions, a bewildering array of new particles spewed forth. They had strange names and even stranger properties. There were pions and kaons, lambdas and sigmas, deltas and xis. They were all unstable, living for fractions of a second before decaying into other, more familiar particles. It was a zoo, a particle zoo, and physicists were the bewildered zookeepers, discovering a new species every week, with no understanding of how they were related, no blueprint for the ecosystem they inhabited. Was nature truly this random, this needlessly complicated? It felt like a betrayal of a fundamental faith in science, the belief that underneath complexity lies a simple, elegant order. Where was the pattern? Where was the organizing principle? Into this chaos stepped a man named Murray Gell-Mann. He was a scientist, but he was also a linguist, a polymath, a man in love with patterns, whether in the grammar of human language or the behavior of subatomic particles. He looked upon the particle zoo not with despair, but with the thrill of a cryptographer facing an unbroken code. He believed there had to be a hidden symmetry, a secret grammar that governed this explosion of transient beings. Working with others, and in parallel with another brilliant physicist named George Zweig, Gell-Mann began to arrange the particles. He grouped them by their properties, like their mass, their electric charge, and a newly conceived property he called strangeness, a whimsical name for the unexpectedly long lifetimes of some of these new particles. Slowly, a stunning pattern emerged. The particles fell into elegant geometric families. Groups of 8, groups of 10. He called this organizational scheme the Eightfold Way, a nod to the teachings of Buddhism. It was as beautiful and as predictive as the periodic table of elements had been for chemistry a century earlier. It suggested that all these dozens of different particles in the zoo were not fundamental at all. They were composite. They were arrangements of something even smaller, even more fundamental. Gell-Mann's mathematics told him that this entire beautiful pattern could be explained if you assumed all these particles were built from just 3 more elementary entities. Zweig, working independently at CERN, came to the same conclusion, calling his proposed particles aces. Gell-Mann, however, needed a name. And for this, he turned not to classical mythology or sober scientific tradition, but to literature, to the dense, dreamlike prose of James Joyce's Finnegan's Wake. He plucked a line from that famously obscure book, 3 Quarks from Mustermark. Quark. The word was playful, strange, almost nonsensical, and it stuck. So the idea was born. The dozens of particles in the zoo were just different combinations of 3 types of quarks, which Gell-Mann initially named up, down, and strange. A proton, for instance, was 2 ups and a down. A neutron was 2 downs and an up. The other, more exotic particles were different combinations, some involving the strange quark. It was a theory of breathtaking elegance and simplicity. It tamed the particle zoo. It turned the jungle into a garden. But it came with a paradox, a colossal, glaring, and deeply troubling problem that would haunt physics for the next decade. If protons and neutrons and all these other particles are made of quarks, then it should be possible to break one open and get a quark out. It should be simple. You just hit a proton hard enough. You smash it with enough energy, and surely one of its constituent parts will come flying out for you to see, to measure, to prove that it is real. So they tried. They built more powerful accelerators. They slammed protons into targets with unimaginable force. They sifted through the debris of these cataclysmic collisions with detectors of exquisite sensitivity. And they found nothing. No free quark ever appeared. Not once. It was a phantom, a ghost in the equations. The theory worked perfectly. It predicted the existence of new particles, like the omega minus, which was subsequently found, a stunning confirmation of the eightfold way. The mathematics was undeniable. The patterns were real. But the physical objects at the heart of the theory, the quarks themselves, refused to show their faces. The harder they hit the proton, the more energy they pumped into it, the stranger the result became. Instead of knocking a quark loose, the excess energy would simply coalesce, following Einstein's E equals mc squared, and form new particles. New quark-any-quark pairs would spring into existence, immediately binding together to form the familiar mesons and baryons of the particle zoo. It was as if you tried to isolate a single magnetic pole by cutting a bar magnet in half. You don't get a north pole and a south pole. You just get two smaller magnets, each with its own north and south. The universe seemed to abhor the idea of a naked quark, just as it abhorred a naked magnetic monopole. This was the core problem. The birth of the idea was also the birth of the paradox. How can something be a building block if you can never hold one in your hand? How can a prisoner be real if you can never, ever see them outside their cell? What kind of reality was this? What kind of fundamental particle was this that denied its own existence as a separate entity? Physics had encountered something new. Not just a new particle, but a new kind of being, a new rule for existence. To solve this mystery, a new theory was needed. A theory that could explain this bizarre imprisonment. And in doing so, it would reveal a force of nature so strange, so unlike anything we experience in our daily lives, that would forever change our understanding of what it means to be a thing. Let us now dive deeper into the world of the quark. Let's try to map this unseen territory. The initial triplet of quarks, up, down, and strange, was not the end of the story. As energies grew higher and experiments became more refined, it became clear that the family was larger. Like a periodic table that revealed new rows over time, the standard model of particle physics grew to include 6 quarks in total. They come in 3 pairs or generations. There's the first generation, the up and the down. These are the most common, the most stable. They're the quarks that build the protons and neutrons of every atom in the universe you see around you. They are the bedrock of ordinary matter. Then there is the second generation, the charm and the strange. They are heavier, more exotic, and unstable. They existed in abundance in the fiery heat of the early universe, and we can still create them today in our particle accelerators. But they decay in a fraction of a second into their lighter up and down cousins. They are fleeting echoes of a more violent past. And finally, the third generation, the top and the bottom, these are titans. The top quark, in particular, is astonishingly massive, as heavy as an entire atom of gold, yet it is a single, fundamental particle. It is so unstable that its lifetime is almost incomprehensibly short. Decaying before it can even form a bond with other quarks. It is the ghostliest of them all, a flicker of immense potential that vanishes almost instantly. 6 quarks, 6 flavors, as physicists call them, a term that, like strangeness and charm, betrays a certain poetic whimsy in the face of the bizarre. These flavors are the ingredients list for the universe's matter, but they are not the full story. There is another property, one even stranger than flavor, a property that is the key to understanding their permanent confinement. It is a property called color. This has nothing to do with the colors you see with your eyes. It is a metaphor. It is a name for a new kind of charge. Just as particles can have a positive or negative electric charge, quarks possess a color charge, And where electric charge comes in two types, plus and minus, color charge comes in three. Physicists, again with a poetic touch, name them red, green, and blue. Every quark carries one of these three color charges. And for every quark, there's an antiquark which carries an anti-color, anti-red, anti-green, or anti-blue. And here is the fundamental rule of this new reality. It is the law from which everything else flows. Nature will not permit any object that has a net color charge to exist freely. Every single particle that you can observe in the universe must be color neutral. It must be white. How do you make white? You can combine a red, a green, and a blue quark, like the three colors of light on a screen, to make a color-neutral particle. This is a baryon. This is what a proton is. This is what a neutron is. Three quarks, each a different color, bound together in a perfect, colorless harmony. Or you can combine a color and its anticolor. A red quark and an anti-red antiquark, for instance. This combination is also color-neutral. This is a meson, one of the fleeting particles from the particle zoo. This is the rule, the absolute, unbending law of the subatomic world. You can only exist in the wild if you're colorless. And this rule is enforced by the most powerful and strangest of all the fundamental forces. It is called the strong nuclear force. You're familiar with other forces. You feel gravity pinning you to the earth. You see light, which is a manifestation of the electromagnetic force. These forces have a familiar behavior. They get weaker with distance. The further you are from the earth, the weaker its gravitational pull. The further you are from a light bulb, the dimmer its light. The strong force laughs at this logic. It does the exact opposite. The force between two quarks, the force that binds them together, does not weaken with distance. It grows stronger, infinitely stronger. Imagine two quarks bound together by something like a cosmic rubber band. When they're very close to each other, inside the tight confines of a proton, the rubber band is slack. The quarks can jiggle around, almost as if they were free. Physicists call this asymptotic freedom. It is a strange kind of liberty that exists only within the walls of the prison. But now, try to pull them apart. Try to stretch that rubber band. As the distance between the quarks increases, the force pulling them back together does not decrease. It remains constant, and the energy stored in the band, the force field, grows and grows. You pull harder and harder, pouring immense energy into this stretching field. You are determined to snap the band and free the quark. But the band is unbreakable. The energy you pour into the field reaches a critical point, and then something extraordinary happens. The energy itself congeals into matter. Out of the vacuum, a new quark and a new antiquark are born. The new antiquark immediately binds to the quark you were trying to pull away, forming a new, colorless meson. The new quark binds to the one you left behind. The rubber band has snapped, but not in the way you intended. Instead of freeing the prisoner, you have simply created two new prisons. You started with one proton, and now you have a proton and a meson. You have not isolated a quark. You have just created more ordinary, colorless matter. This is the mechanism of confinement. This is why no free quark has ever been seen. The force that binds them is literally creative. The energy required to separate them is infinite, because long before you could reach infinity, you would have supplied enough energy to create a whole universe of new particles. So how do we know they are there? If we can never see one, how can we be so sure? We know because of the shadows they cast. We know because of the fingerprints they leave at the scene of the crime. In the late 1960s, at the Stanford Linear Accelerator Center, physicists conducted a series of landmark experiments. They used a powerful electron beam as a probe. They fired these electrons, which are truly fundamental particles as far as we know, at protons. This was like firing tiny precision bullets into a mysterious, fog-filled room to figure out what was inside. If the proton were just a uniform, amorphous blob of positive charge, the electrons should have mostly passed through or been deflected gently. But that is not what happened. Occasionally, an electron would be deflected at a shockingly sharp angle. It would recoil violently, as if it had struck something small, hard, and point-like deep inside the proton. These were the quarks. We could not see the quark itself, but we could see the ricochet of the bullet that had hit it. It was like seeing shadows on the wall of Plato's cave. The data from these deep, inelastic scattering experiments was the undeniable evidence that the proton was not fundamental. It had internal structure. It had tiny, hard constituents rattling around inside. The ghosts in the machine had left their fingerprints. The prisoners were real. Their chains were just unbreakable. Now we must pause. We have journeyed deep into the mechanics of this hidden world. We have learned its rules, its taxonomy, its strange forces. But in doing so, we have come face to face with the paradox in its most amplified form. Consider what this means. The defining feature of a quark is its color charge, red, green, or blue. But we can never observe this property directly, because any observable particle must be colorless or white. The very property that makes a quark is eternally hidden from view. It is an essential attribute that can never be measured in isolation. This is profoundly unsettling. It challenges our very notion of what a property is. Is a property that can never be seen a real property at all? Furthermore, we have the phenomenon of confinement itself. This is not just a detail. It is a radical departure from every classical intuition we have about the world. In our world, things are divisible. You have a house. It is made of bricks. You can take a brick out of the wall. The brick exists, and the wall with the hole in it exists. The part is separable from the whole. The universe, at its most fundamental level, says no. The proton is a whole. Its quarks are its parts, but you cannot remove a part. The existence of the quark is conditional. It is contingent upon its relationship with its fellow prisoners. A quark only has meaning. It only is as part of a colorless collective. Ask yourself, what is a red quark? It is a thing that must find a blue and a green to exist. Its identity is not internal, it is relational. Its being is defined by what it is not, by the other colors it requires to achieve neutrality, to be allowed to participate in reality. This violates the classical law of identity, the idea that a thing is just itself, A equals A. Here, a quark is not just a quark. It is 1/3 of a proton. Its existence is borrowed, shared, eternally entangled with its partners. This concept of entanglement is usually associated with the more famous paradoxes of quantum mechanics, like the spooky action at a distance that so troubled Einstein. The idea that two particles can be linked, so that measuring one instantly influences the other, no matter how far apart they are. Quark confinement is a form of entanglement taken to its absolute extreme. The entanglement is so strong, the connection so unbreakable, that the concept of distance between them becomes almost meaningless. The bond itself is more real than the things being bonded. The relationship precedes the individual. And what of our role in all of this? What is the role of the observer? In much of quantum mechanics, there is the famous measurement problem. The act of observing a quantum system forces it to collapse from a state of many possibilities into a single, definite reality. An electron's position is a cloud of probability, but the moment you measure it, it is here. The observer seems to play a crucial role in the creation of the definite. In the world of quarks, this takes on a new and powerful dimension. When we try to observe a single quark by hitting it with immense energy, what happens? We do not see the quark. Our act of observation, the very energy we inject to get a glimpse, actively creates new reality. It pulls new particles, new mesons, out of the vacuum. The universe does not just hide the quark from us. It responds to our intrusive questions by changing the subject. It answers our attempt to isolate a part by creating more holes. It insists, with force and creativity, that we are asking the wrong question. It refuses to let us break its most fundamental rule. Reality, it seems, is not a passive stage to be inspected. It is an active participant in our inquiry. It has a point of view, and its point of view is that some things are not meant to be alone. This is the precipice. We stand at the edge of physics, and peer into the abyss of philosophy. The rules we have uncovered are not just about tiny, exotic particles. They're the rules of the substance from which you are made. So let us bring this journey home. Let us bring it from the heart of the proton to the heart of your own being. You're made of atoms, trillions upon trillions of them. Each atom has a nucleus. Each nucleus is made of protons and neutrons. And every single one of those protons and neutrons, right now, within you, is a tiny, perfect prison, a colorless collective of 3 quarks, bound by the unbreakable rubber bands of the strong force. You're not made of solid things. You're not a collection of tiny spheres. You're built from ghosts. You are constructed from prisoners. The stability of your body, the integrity of your cells, the very fact that you do not dissolve into a mist of radiation is owed to this strange law of eternal confinement. The solidity you feel is the frantic, energetic dance of trapped quarks and the powerful force field that holds them captive. You are a symphony of relationships, a standing wave of inseparable parts. The quarks that constitute you have no independent existence. They're defined only by their connection to each other. Their reality is a shared reality. Does this not change your perception of yourself? You think of yourself as a single, unified being, an individual, but you're a community. You are a universe of collectives, each one a testament to the principle that the whole is more fundamental than the part. This forces us to ask a terrifying and exhilarating question. What does it even mean to be real? Our common sense notion of reality is tied to objecthood. A thing is real if it has distinct properties, if it has boundaries, if it can be isolated and pointed to. A chair is real. A rock is real. We believed a proton was real in this way. We wanted the quark to be real in this way. But the universe is telling us that our definition of real is too naive. It is a provincial prejudice of the macroscopic world. Is a quark real? It has mass. It has charge. It has spin. It deflects electrons. Its existence is required by a theory of breathtaking predictive power. But it can never be put in a bottle. It can never be alone. Perhaps the quark is not the real thing. Perhaps the force field, the rubber band between them, is what is real. The quarks are just the endpoints where the field is anchored. In this view, matter is not a substance. It is a manifestation of bound energy. It is a knot in the fabric of a force field. You are not made of particles. You are made of patterned energy. Or perhaps the relationship itself is the only real thing. The colorless state. The trinity of red, green, and blue. That harmony is the fundamental entity, and the term quark is just a label we give to the vertices of that relationship. Reality, at its base, might not be a noun. It might be a verb, an ongoing process of binding and relating. This is the profound philosophical shift demanded by the physics of the strong force. It asks us to abandon our obsession with substance and learn to see the primacy of structure, pattern, and relationship. The world is not made of bricks. It is woven from threads of connection, and the things we see are just the stable patterns of the weave. And if we are willing to take one last speculative leap, where might this lead us? Consider your own consciousness. The feeling of being you, it is a unified experience. You are not a jumble of disconnected sensations, thoughts, and memories. You are a single self. There is an I that seems to preside over the chaos. Modern neuroscience tries to break this down to find the consciousness module in the brain, and it fails. It finds that consciousness is a distributed, holistic process emerging from the complex interplay of billions of neurons. It cannot be isolated. It cannot be pinned down to a single part. Is it not a haunting echo? Could the unified nature of our subjective experience be a macroscopic reflection of the universe's most fundamental organizing principle? The principle of confinement. The principle that true reality emerges from the inseparable union of parts. Could our sense of self be a stable resonance, a large-scale version of the colorless harmony that governs the heart of every atom inside us? Perhaps the I that you feel is real is not a thing, but a relationship, an unbreakable bond woven from the threads of neurological activity, just as the proton is an unbreakable bond woven from the gluonic field. Perhaps consciousness, like the proton, is a whole that is irreducible to its parts. This is speculation. Is poetry built on the foundation of physics? But it is a way of seeing how the deepest laws of the universe might not just govern the world out there, but might also resonate within the structure of our own minds, our own being. The mystery of matter and the mystery of consciousness might not be two separate questions. And so, we return to where we began. We return to the central, simple question. After this long journey through particle zoos and color charges, through unbreakable bonds and creative forces, what is the answer? Are quarks real? You must see now that the question itself is the problem. It carries within it the baggage of a classical world, a world of separable things that the universe, at its deepest level, has abandoned. Asking if a quark is real is like asking about the sound of one hand clapping. The question assumes a context that does not exist. A quark is as real as a shadow. A shadow is not nothing. It is the absence of light, and it tells you something true about the object that casts it. A quark is as real as a thought. A thought has no mass and no location, but it can change the world. A quark is as real as the North Pole of a magnet. It is an inseparable aspect of a greater whole. The better question is not what is a quark, but what does a quark do? And the answer to that is astonishing. It conspires with its partners in an eternal, intimate dance. It submits to a law of absolute togetherness. And in doing so, it builds a proton. It builds a nucleus. It builds an atom. It builds you. The ultimate truth revealed by this journey is not about a particle. It is about a principle. The principle of confinement. The principle that reality is born from connection. This is the final, unifying metaphor. The universe is not a work of architecture, built from stacked bricks. It is a work of music. The quarks are the individual notes, but a single note played in isolation has little meaning. The true beauty, the reality of the piece, lies in the chords, the harmonies, the relationships between the notes. The proton is a stable, three-note chord. The mesons are fleeting, two-note harmonies. And the entire universe, all of matter, is a grand and complex symphony playing out according to these rules of harmonic composition. Confinement is not a prison. It is the principle of music itself. It is the law that insists notes must be played together to create something more than themselves. It is the poetry of the cosmos, a poetry that insists on unity, on relationship, on the indivisible whole. And you're a part of this music. Look at your hand one last time. It is not a thing. It is a chord. It is a sustained passage in the symphony of existence. The feeling of solidity is the feeling of its harmony. The boundaries you perceive are the edges of its resonance. The mystery is not that the universe is built from invisible, paradoxical things. The mystery is that these things, through their strange and beautiful laws, conspire to build a being that can look back upon the universe and wonder about its own construction. You are not an observer of the cosmic music. You are the music, a temporary, thinking, feeling, wondering piece of the symphony. And the quarks within you are not prisoners. They are willing participants in the song that is you. They are the notes, but you are the meaning that emerges from their perfect, unbreakable, and eternal togetherness. The mystery is not out there. It has been inside you all along.